In this section, we will discuss piezoelectric anisotropy, and we'll use this also to explain and define what these different piezoelectric coefficients that you see in the matrix, piezoelectric matrix are doing. So as an illustration, let's look at quartz crystal. It has structure 3,2. I will explain a little bit about this notation. I think you know it from crystallography. But if you look the crystal structure of quartz from different direction along x-axis, z-axis, and 1, axis, you see the structure looks very different. The distribution of atoms is different, and that means that properties are most likely also to be different along these different directions. And that indeed turns out piezoelectric coefficients along these different directions are different, and along some directions they may even be zero. Let's spend a little bit of time on and explain these different piezoelectric coefficients, longitudinal, transverse, and shear by using as an example perovskite structure. Perovskite structure, which I think you should be familiar with, but if you are not, here is the basic description. So these are ABO3 crystals. Not every ABO3 crystal is perovskite. For example, lithium niobate is not perovskite, although it has the same structure. In perovskite structure, you have that large A cation is on the corners of the cube, B atoms is in the center, and oxygen or another anion creates this octaeder, which is characteristic of perovskite structure. The one that I'm drawing here is tetragonal, where the central atom is shifted a little bit with respect to oxygen atoms, and oxygen octaedra is also shifted with respect to A atoms, and so we have a polarization in this structure. Polarization is not required for a piezoelectric effect. We will discuss later on what are the requirements, symmetry requirements to have piezoelectric effect. But in this particular structure it is, and it's easier to explain it, to explain these different elements in this structure. So if you are looking at point group 4 perovskite material, I would like to explain what these symbols for MM mean. The 4 means that the crystal along this axis have a fourfold rotation symmetry. That means that if I have a fourfold symmetry here, that means that rotation around that axis will bring the crystal to repeat itself. So if I rotate A into B, I will have exactly the same structure, and since I do it, I can do it 4 times and repeat the structure. Then there is a mirror plane in this direction and in this direction. So these are mirror planes. The crystal exactly repeats itself. So there is an M structure, M mirror plane here and here, and fourfold symmetry in this direction, and the crystal is identical on these sides. And that has implications on how piezoelectric coefficient looks like. So let's look at D33 piezoelectric coefficient. So in this matrix of piezoelectric coefficients, we have here D11 and here would be D33. Sorry, I apologize. So in this matrix that looks like this, this is D11, D12 to D16, then we have D21, D22, then we have D31, D32, and D33, and then other shear coefficients, and we want to look at this D33 coefficient. So the way this okay, I want to delete this. So we have this axis along z axis, along the polar axis. We can rotate 4 times. So this is x1, this is x2, and this is x3 or z. So if we are talking about D33 coefficient, that means that we are looking, if we are looking at direct piezoelectric effect, that means that we are applying force pressure along axis 3. So we apply pressure like this, tensile or compressive, and we measure charge that is created on this face, and that charge is described by D33 coefficient, one index 3 for stress and the other index 3 for pressure. And obviously once I stretch or contract this crystal, this polarization, this dipole moment will change, and that will give you some charge or some change in the charge. Remember, piezoelectric coefficient is change of charge with respect to pressure. So that dipole moment will change and we will have some pressure. But let's see what happens along x1 if we apply pressure in this direction along x1. Again, we will change that dipole moment. What sort of coefficient we are talking now? Well, we are applying pressure along sigma 1. We measure charge still on this face. So we apply pressure in this direction. We change this dipole and we measure pressure here perpendicular to x3 or z axis. So that would be the D31 coefficient. Okay. Now, if we do same along x2 axis, so we apply pressure along x2 axis. Since there is a 90-degree symmetry here, rotation of the crystal by 90 degrees will repeat crystal, we must get everything same along x1 and along x2. So if we look at D3 under pressure applied along sigma 2 on face, which is now sigma 2, we will get D32 coefficient. But those two coefficients must be the same because there is no difference between direction x1 and that face and direction x2 and that face. So we see immediately that D31 must be exactly equal to D32 in this structure. And we can go like this, taking into account symmetry of the crystal and derive a relationship with the dependencies between different coefficients, relationships between them. This can be done, as I will show you later, rigorously mathematically also, but it's good to see that it can be done like this qualitatively, which allows for easy understanding what these different coefficients are doing and how they are interrelated. So for this crystal, for 4mm symmetry, we will get that we have polarization only along direction 3. So pyroelectric coefficient has only a P3 component. We will get that the electric permittivity has only 3 non-zero elements and all other are 0. Piezoelectric coefficient has only 3 elements. 2 of them are equal, and then has 2 shear coefficients which are also equal. For converse effect, we have the same, just transpose matrix, and also for elastic constants, we have a large number of elements, most of which are, many of which are 0, and then some of them are related. For example, S11 and S12 and S22 must be the same for the same reason that we just said. How can we see, for example, that D11 is 0 for this perovskite structure? Well, that means that we apply pressure in this direction along axis 1, and we measure charge developed on this face. Well, when we stretch the crystal like this, there will be change of dipole moment in direction x3, but there will be no creation of a new dipole along direction 1. And that means that, D1, sigma 1, so we apply pressure along sigma 1. We measure on that same surface charge, so charge density on that surface, that's D11 coefficient, and it is 0. And as I said, this can be shown rigorously for this symmetry. So many piezoelectric elements turn out actually to be 0, and we have only 3 independent. Now this structure is important because many ferroelectric, piezoelectric materials have this structure, and very importantly, poled non-oriented polycrystalline materials, ceramics, polarized ceramics, as you will see later, also have that same structure, with the difference that one coefficient is different for 4mm and for 6mm, and ceramics. I will explain this infinity symmetry axis later on. So we would have here S66 for 4mm, I think, and for 6mm and infinity mm, we would have that term is equal to S12 minus S11 minus S12 times 2, I think. Now, we have just derived, we see that in perovskite materials for 4mm and some other groups, we have this matrix for a D coefficient, and we know that we also have G, H, and E coefficients, and they would all have this same elements in their piezoelectric, non-zero elements in their piezoelectric matrix, and also the same pairs of them would be equal. This line which is connecting two elements means that they are equal. However, there are symmetries in which, for example, D and E are not equal. And one example is, I think, 3M group, in which D coefficient has this term 2, while E coefficient doesn't. So this is interesting. That's because of the strain. You know that in strain and stress we have this factor of 2, and in some of these matrices the shape of the matrix, some point groups, the form of these matrices is not exactly the same. this is something that has unfortunately been made a mistake about, even in some textbooks. And here is an example. This is a textbook in which there is an error in these E coefficients. The reason for that is that some of the optical tensors are also third rank, and people in this particular book assumed that optical and piezoelectric tensors of third rank must have exactly the same shape of the of these tensors and matrices, and that's not always the case. So just be careful about that. Now, we said that there are only 3 different kind of coefficients for in 4mm structure. So there is only one shear coefficient, independent shear coefficient. There is 2 what we call transverse, 2 what we call transverse, and one of them which is longitudinal. So let's explain them. So here is a D33 coefficient, that's longitudinal effect. Why longitudinal? Because we are applying pressure along the same axis where the surface on which we measure pressure is placed. So here is the surface, it's perpendicular to this axis, and therefore we have 2 same indices. This is called longitudinal piezoelectric effect. Here is illustration of the direct, and here is an illustration of the converse piezoelectric effect. Then we have a so-called transverse effect, in which we are applying pressure along axis 1 and reading charge again along at the surface which is perpendicular to x3. So that's D31 coefficient or D32. They are identical, same, numerically same in Perovskite 4mm structure. And very interesting is so-called shear coefficient, in which we are applying a shear, okay, and we will cause polarization to rotate, the crystal cell to rotate, and therefore instead of creating a new charge or causing charge difference in z-axis, we will actually have that charge will be created, or will go from 0 to some value on these axes that are parallel to 3 axes, and that's sigma D15 coefficient. So if you apply pressure, you will create charge here, and if you apply electrical voltage, the crystal cell will deform in this way. You can write it like this. So D1 is equal to D15 sigma 5, and sigma 5 is equal to sigma 2 1 or sigma 1 2. So it's the force along direction 2 or 1, and we are looking at the pressure at the face charge which is perpendicular to that direction. So shear coefficients are very important. They are very large, as you will see. They are larger than longitudinal and transverse in almost all materials when we look coefficients, define coefficients with respect to crystallographic axis. But if you look at the value of piezoelectric coefficient in some other direction, you will find out that this is not the case, and D15 can be small and D33 can be large, but we will discuss that later on. So what I would like to ask you is to draw yourself this, convince yourself that this is D15. Indeed, when I was explaining it here, I think I might have said it wrongly, and you should make it clear for you. These indices that I have written here are correct, but actually it's not. Let me correct that. So yes, so this is wrong. So let's go here. So D15 coefficient. So charge is 1, and 5 is actually 1, 3, and 3, 1, and not 2, 1. Okay. So if we go with this, if this is direction 1 and this is direction 3, then I am looking for a charge created at these faces, and D31 is, or D13 is along on the face which force is applied along direction 1 at a face which is perpendicular to axis 3. So this is correct. So if you rewind your video, it's I had it wrong the first time, and this is correct. So this is yes, there is another piezoelectric coefficient that I would like to introduce, and that is so-called hydrostatic piezoelectric coefficient, which is also very important for some applications like sonars, underwater, deep underwater, at a normal wavelengths, the pressure that is that crystal sees, sonar sees, is hydrostatic. It's same in all directions. That's because the acoustical wavelength is very large, normally very large, and also the pressure, the static pressure in the material is very large, and therefore we will have this static. We will have that sigma 1 is equal to sigma 2 equal to sigma 3 and equal to hydrostatic pressure. So the only components are these, and then if we calculate D3, it will be 2 times D31 plus D33. So we multiply this by that, and this combination 2 D31 plus D33 is equal to hydrostatic piezoelectric coefficient. Now it turns out that D33 is positive while D31 is negative. And 2 times negative D31 is almost the same as D33, so this coefficient becomes very close to 0. Still sonars work very well, and we will see later on how you can make this hydrostatic coefficient larger. Why should D31 be negative and D3 positive? So let's say that this here is a D33, that in this crystal tensile strain will give in direction of polarization positive change of the charge will increase polarization, will negative on the other side. Now, when we apply, so crystal would extend when we apply pressure. When we apply pressure in this direction, also tensile pressure on that same piece, then crystal will deform like that. And the polarization will be smaller, so the coefficient will be negative. However, this doesn't always have to be the case. There are materials in which so normally D31 is less than 0, but there are materials in which D31 can be bigger than 0, and one of them is certain crystal cuts of well-known ferroelectric lead titanate, and also some ceramics based on lead titanate have positive D31, small but positive D31. So this is what I wanted to tell you a little bit about piezoelectric anisotropy. We will come to this topic later on several times. It's very important for most performant piezoelectric materials, relaxor ferroelectrics. And I also wanted to define these three most important piezoelectric coefficients: transverse, shear, and longitudinal in perovskite materials, which we will discuss the most. You will see that in some other structures which are also important, like rhomboedral in relaxor ferroelectrics, we will have other shear coefficients. In orthorhombic materials, you can have different D31 and D32 and so on. But for those of you who are encountering these sort of things for the first time, looking at 4mm perovskite structure is really convenient to understand everything. So this is end of this section.